So the EFAS reporting points have been operational on the EFAS Map Viewer for a long time. In June this year, we launched EFAS version 4.4, and in this release, we made some updates to how the reporting points are generated and in the projects shown on the web map viewer. I will talk you through the updated features on the web layer in this demo. Right. So the EFAS reporting points layer shows locations on the least flood river network for which detailed information on the forecast is provided. Most of those locations are where partners have shared discharge data with EFAS Hydrological Data Collection Center. At the time of this webinar, we have 3,337 of what we called fixed reporting points. And we would like to take this opportunity to thank all our partners for contributing to EFAS. And zooming here into the Ebro Basin in northern Spain, you can see the fixed reporting points for which no flood condition is predicted as gray or blue squares. The blue reporting points correspond to a station where their medium-range forecast is post-processed at a daily time step. When there are flood conditions and the EFAS reporting point criteria are fulfilled, these gray and blue squares change in color. And depending on the severity of the forecast, those points can be colored in yellow, red, and from EFAS 4.4 also purple. The three colors represent an expected exceedance of the 2, 5, or 20-year return period thresholds for that location. If that flood severity is forecasted within the next 48 hours, as shown here, a bold black border will surround the reporting points. Another feature of the reporting point layer regards the stations with upstream areas that are too small to meet the EFAS notification criteria, but are available in the list of fixed reporting points provided by partners. When forecasts are exceeding the 2, 5, or 20-year return period threshold, those points are highlighted with a color-coded border, as seen for this example in Pamplona, where it exceeds the 20-year return period. This feature allows partners to monitor their own stations, even if on very small catchments. Here we can easily identify a station through the search feature, which then zooms to that chosen location. Clicking on the selected reporting points, the pop-up window appears, and for these stations in the Ebro River in Zaragoza, Spain, EFAS receives discharge data in near real time. Hence, the medium-range forecast can be post-processed. When this is possible, the first graph shown on the pop-up window is the post-processed hydrograph, and the post-processing model remains at 24-hour time step as introduced in EFAS 4.0. The river discharge forecast hydrograph, which comes after the post-processed one, shows information on both cubic meters per second scale, but as well on the return period scale, as you can see just now. And you can see that for the river discharge forecast forced with ECMWF ensemble data, the hydrograph is produced at 6-hour time step, comparable to the one produced with Cosmo. And this feature was introduced back in 2020. The hydrograph also shows outputs from the model forced with observed precipitation and air temperature produced at 6-hour time steps, those black dots in the beginning. The hydrographs are scaled according to the local return period thresholds. And the supporting plots of imported model variables named upstream precipitation and snowmelt and average temperature are shown with additional information with initial conditions and uncertainty in the forecast. These plots should make it clearer to diagnose the driving force behind the hydrological forecast. Next is the forecast overview table, which was majorly revamped to be more aligned with other products. First, we now use a single color scheme for both deterministic and ensemble forecasts, with a color gradient for the latter. Second, we merge the ensemble exceedance probabilities into a single row by only showing the maximum probability over the most severe level. We define the most severe level using the same criteria used for the reporting points. Therefore, we only show values above 50% for the 2-year return period threshold and above 30% for 5 and 20-year return periods. Finally, we also added the combined total probability, which allows users to interpret the forecast for a particular location in finer detail. The last section of the reporting point window is where we show the persistence plots with forecast probabilities for each input over the last 6 forecasts and different severity levels. The latest forecast is shown in the top row at the same 6-hourly steps. In river stretches with strong flood signal but without stations, dynamic points are generated, and their base and border colors follow the same rule as for the other reporting points. The only way to identify them is by looking at their information table, where they receive not a station label as a station name. Everything else is the same. Finally, let me show you a new feature of EFAS version 4.4, the flood probability persistence layer. This layer shows the average total probability between the last two model runs with the three combined flood severity levels. As you can see on the legend, it only shows the most severe level that is above certain probability limits, but as we just showed for the overall forecast table for Zaragoza. It is a great summary for the forecast and is the base of the reporting points definition. And we believe that it also helps to interpret the flood forecast evolution along different model runs, as we can see in this example of how the flood signal moves downstream in the Aragon River.